Good morning. We are moving ahead again. So we looked at, what have we done in the course? We've done kinematics. We looked at forces for a couple of chapters. We looked at a close-up look at gravity. And now for the next two chapters, we're going to be discussing energy. So it says here, chapter 7, work and energy. And where this is all headed is the idea of energy. Energy is a word, it's one of those kind of dangerous words in physics because everybody uses the word energy all the time. And in physics, there's as you might expect, there's a very definite definition as to what we mean by energy, and that's what we're going to be looking at. Now, work also is a bit risky because, when you hear the word work, it means, your employment, or you're clocked into whatever task you've been hired to do. So work and energy have specific meanings in physics. We got to take a look at that. And what I want to emphasize here too is energy is the driving concept here. Work, it turns out, is an energy transfer. So, I like to say that, sure, it's spelled W-O-R-K, but it's pronounced energy transfer. It's one of those unusual English words that has an unusual pronunciation to it. So the example we have here is, hey, go A's, right? So here we have this picture with the baseball, and the idea is right now the baseball's at rest, and we want to get the baseball moving. Now, it turns out that a moving baseball, any moving object, has what we call kinetic energy, and that's going to be kind of our first definition of energy. Any object in motion, we say, has a certain amount of kinetic energy. So the idea with this picture is, this picture for the A's is going to exert a force on that baseball. So it's got hold of the baseball, going to start exerting a force on the baseball. Now, in earlier chapters, we would have said, okay, so the baseball has a certain mass, and we're going to exert a force, and there's going to be an acceleration, and it's going to acquire some velocity. And that's all, that's all fine and good. But now what we're going to do is say, when it's moving, it has this property of kinetic energy to it, and the amount of work that the pitcher is doing, and this literally is their employment, right? So they're getting paid to transfer energy to this baseball. The pitcher is going to transfer energy into this baseball by exerting a force. We'll see how that's all related. The pitcher is going to exert a force over a certain displacement. So the pitcher exerts a force and the ball moves. Those two things are going to be important in order to have energy being transferred. So the pitcher exerts a force, the ball begins to move, the pitcher continues to exert a force over some distance, and then finally lets go. During the time the pitcher was exerting a force on that baseball, the pitcher was transferring energy. Let's take a look at some of the some more details on this, but that's kind of where this chapter is headed. We want to be able to identify forces, and you guys are already expert at that, right? We've been identifying forces now since chapter 4 with force diagrams. Energy transfer is the work being done by a force. Let's see. So here's a list of topics. I did want to make sure that we, every time you see the word work, I'm going to highly recommend for at least for the next week or so while you're looking at the at chapter 7 and 8. Every time you see the word work, you got to tell yourself it's an energy transfer that's taking place. These are just the topics that are coming up, so I'm actually going to move on to the next page. Yeah, here's a good example. What do you think? Is this person doing work? Are they transferring energy? And if they're transferring energy, where's the energy being transferred to? You go, well, it's this box, right, or this crate. So we've got this crate on the floor. This person is exerting a force on the crate, and there is actually a displacement that takes place. And we said, oh, those are the two features that we have to look for. Is a force being applied? And is there a displacement in the direction the force is being applied? If so, energy is being transferred. That means the person is doing work. on that object. So the work done by a constant force, we'll start out imagining the forces are just constant, is defined as the distance that the object has moved multiplied by the component of force. I think I'm going to flip that around. So here's a force the person's exerting on that object. Now there's two components. One of those components is horizontal, one of the components is vertical. Now notice that the box, or the crate, it's not displacing in the vertical direction. Now that's not saying the vertical force isn't there, it is, but that vertical force is not transferring any energy. And so we say that vertical force component is not doing any work. The horizontal component, on the other hand, is in the direction that the displacement takes place. So the crate slides from that side of the floor over to the other side of the floor. Now, we've got vector signs on these, and we're going to come back and see this all in terms of vectors. But notice the vector sign on D says that the displacement is happening right along that direction, and it's only the F cosine theta component. It's only that horizontal component that is transferring energy. So when we want to say, how do we pronounce the symbol capital W? Let's see, what does that stand for? Oh yeah, capital W stands for energy transfer. Now another thing that the textbook doesn't do that I think is a good idea, I'm going to highly recommend, is when you're doing the problems and you're calculating the work, I wasn't supposed to say work, energy transfer, when you're calculating the energy transfer taking place, or the work, due to force F, and there's force F right there, that particular force will have an energy transfer of, now I want to move some of these symbols around, it's going to be F times the cosine of theta, because that's the component parallel to the displacement. So we'll take F times the cosine of theta, and then we multiply by the distance. And that turns out to calculate the work, or the energy that's being transferred to that object as it slides along the floor. Okay. Now, what would units be for energy or work? So the units of energy transfer are energy units, and those are joules. Now, the joule is a Newton times a meter. And you go, well, of course, if we're going to exert a force over some displacement, that's going to have units of newtons. That's the force part of the calculation, and then there's a displacement. So literally, a force times a displacement, newtons times meters, gives us energy units, and those are going to be joules. Now, you've probably heard of other energy units, right? There are calories are energy units, kilowatt hours are energy units, BTU are energy units sometimes, it depends on the context. So there's all these different energy units out there, and you know, this is one of those situations where you'd think, yeah, if we could just all get on the same page and use the same units for everything. So the standard unit that we'll be working from, the international system of units, uses joules for energy. So let's take a look at this person now. So before, we were saying, okay, what we're going to have to do in this chapter is we're going to have to continue drawing force diagrams. Look at that. So that's a good thing. You guys are force diagram experts. And so there's three forces that have been identified here. Now there's a gravitational force, and the object we're isolating here is that grocery bag. So there's a grocery bag, has a gravitational force acting on it. There is a force, I don't know, is that a push? Is that what that is? It's a contact force. So the person has their hands out, and they are lifting this object, and the closest thing I have here would be, surprisingly enough, the textbook. So here I am, I'm holding onto this textbook, I am exerting an upward force on my textbook. So there's a gravitational force on the grocery bag, there's a force of the person, contact pushing up on it. Now, there's a force in this, there's a displacement taking place in this direction. So the picture's a little, to me it's a little confusing. What I don't know about this picture is this person at rest, or is this person in constant motion? Is there a constant velocity going on? Because here's what happens. If the person is standing there at rest, they're not doing any work. Now this is where it might seem a little non-intuitive, and you're thinking, wait a minute, if I have a heavy object and somebody says, could you hold it there for a while, and I'm holding this object, and my arms start to get tired, I'm thinking, I am absolutely doing work, but in physics terminology, you're not. And the reason why is there's no displacement taking place. So if the person's at rest, then there's no displacement. The displacement part of that drops out. And the person's not doing work. And you might say, well, wait a minute. Isn't this force of lifting the groceries, that's got to be involved with energy somehow? And it turns out it's not. And the reason why is, this grocery bag is at rest, and it stays at rest. I'm not transferring any energy to it. If I was transferring energy to it, it would be going faster. Okay, so that would require some kind of an energy transfer, but if it's just sitting there at rest, or if I'm moving at constant velocity, that's the other possibility here. What if I'm moving at constant velocity? Well, if we're moving at constant velocity, that still doesn't require a force in that direction. So whether the person is at rest, or whether this is a picture of a person moving at constant velocity, that's not going to require a force in that direction. And the force that you're lifting upwards with, there's no displacement in that direction. What about gravity? Is gravity doing any work? No, gravity's not doing any work either, because there's no displacement in the direction of the gravitational force. So what I would want to do then is I would want to come back and coming back to, well, let's just work from the diagram we have here. So there's no displacement in this direction, so the work, the energy transfer being done by mg is 0. There's no displacement in this direction, so the force being done by the person lifting, there's no energy transfer there either. If it's constant velocity, let's see what they're saying, as long as the person does not lift or lower the bag, there is no work. The force exerted has no component. Yeah, so these forces remain vertical. Now, I'm thinking there is a period when they're actually doing work on these bag of groceries, and that would be during the time when there's an acceleration taking place. So if the person's holding the bag and then they begin moving, during that period of time, and maybe it's a short period of time, but during the period of time where the object is accelerated forward, there would be a force component in that direction. So it's some kind of a contact force with the person, right? The person leans the bag forward and pushes it. There's going to be a component here. That's going to transfer energy. Now, once the person is up to their normal walking speed, then the energy transfer stops. So remember, we talked about kinetic energy. When objects are moving, they have kinetic energy. Right now, there's no kinetic energy if the person's at rest. But when the person begins to pick up speed, during that period of acceleration, energy is being transferred in, and the kinetic energy is going up. Now, when the person hits their cruising speed, then the energy transfer stops. So the displacement can continue, but if there's no force in the direction of displacement, then there's no work being done. There's no additional energy being transferred into that object. All right. So it's a kind of a funny set of rules. It may be a little non-intuitive, and part of that's because we're using the words work and energy. But this is how work and energy transfers are defined in physics. So here we have, let's go back to that picture. Here is that crate again, and let's put some numbers in. So what this picture is showing is that we have a force, F sub P, so there's a force a person's pulling with. There's a gravitational force, there's a normal force. Now, what's kind of interesting here is they don't have friction yet, but we'll get to that. So it's a force diagram, and we're used to drawing the force diagrams. And now what we want to do is, well, let's read the problem. I know, that's the starting point always, is read the problem carefully. So what's the important information here? So we've got somebody pulling a crate. It's 50 kilograms. And it's a good distance. It's 40 meters, and it's along a floor that's level. So we're not raising, we're not going up a ramp, we're just going level. And the force that's being applied is 100 newtons. And the force acts at an angle of 37 degrees. The floor is smooth and exerts no friction. They did say no friction. Okay. So they came right out and said no. Sometimes they just say the floor is smooth, and then, the idea is there's not going to... But they came right out, explicitly no friction. Determine, A, the work done by each force acting on the crate. And I think that is so important. So I don't think our textbook emphasizes that enough. I've tried to select homework problems where they ask you to, put together a list. What are all the forces and how much work or how much energy is being transferred by each one of the forces? List each force and identify how much work, how much energy is being transferred. And then in B it says find the net work. So it sounds like, well, let's do a list. So what forces do we have? What about this normal force? Now the normal force is in this direction. Is there any displacement in that direction? And you go, no. The crate's just going in the x direction. The normal force is exclusively in the y. A force in the y direction is not transferring energy if the displacement is only in the x. Now, if that force were to lift the object upwards, then we would have to go in and rethink about the work being done. But as is, the only displacement here is in the x direction. So normal force is doing no energy transfer, no work. The gravitational force, no energy transfer, no work. That would change if we were on an incline, right? But for a level floor, mg is not transferring any work if the crate maintains that horizontal motion. Now this force, the force that the person's pulling with, we saw this in the previous diagram, this could be divided into components. So this would have a horizontal component and a vertical component. Vertical component is not doing any work, but the horizontal component is. So you can see what happens in these diagrams, maybe there's 3, 4, 5 forces that we have to take a look at. And in many cases, the majority of those forces are not transferring any energy. And that's fine. You just write a 0. You go, in this case, 0 energy is being transferred by this force, and you move on to the work being done by the others. So let's see what this looks like. So here is my force diagram. There are my forces, mg. Here's the crate, normal force. Here's the force the person's pulling with. And here is, now the angle they gave us was 37 degrees. There's all my given information, the stuff that we had listed and read from the problem. The force is in this direction, so I'm going to get a horizontal component. I'm going to get a vertical component. And we do successfully then have the object sliding across the floor. Now, the distance that travels is 40 meters. So here we go. Let's see, what forces do we have? So I want to say, first of all, let's list all of the forces. N, mg, F sine theta, F cosine theta. So I would say break things into components and list the individual components on your table that you've put together. I think it's an easier way to do this because what you can do then is you can just go, okay, 0, 0, 0. And why did these 3 forces end up with not transferring any energy? Why did they not end up doing any work on the crate. And that's because if we take them one by one, N was in the positive Y direction, displacement's in the X, so at 90 degrees that's not going to transfer any work. Gravity's in the negative Y direction, but the displacement's in the X, that's not going to do any work. F sine theta is in the vertical direction, X is horizontal, no work. The only place where we have energy transfer taking place is with the F cosine theta component times X. So force times displacement. So that's what I did here. So 0, 0, 0, and then F cosine theta times D. I think that's the easiest way to organize the information and identify which components are transferring energy, which ones are not. So let's calculate that. Let's see, F cosine theta, that was 100 newtons of force, but it was only the cosine theta component, so that's going to reduce that number. It turns out F cosine theta is 80 newtons. So 80 newtons of force went into moving this object horizontally, and then to turn that into energy transfer, and there should be a subscript here because I just told you guys that should have a subscript F, that should have a subscript F. W sub F is equal to 80 newtons times 40 meters, and I can do the units first. Newtons times meters, that's going to be joules. So joules are units of energy, and multiplying the 80 times the 40 gives us 3,200 joules of energy that have transferred into that object. Now, what does that mean to say that we've transferred the energy in? Well, if this object is frictionless, we know this from previous chapters. If we're exerting a force on something, it's going to accelerate. Now, I've got 80 newtons of force in this direction, and I have 0 newtons of force opposing because we decided it was a frictionless surface. This thing's going to be moving, and it's going to have a kinetic energy of 3,200 joules. So in this case, all of that energy transfer went into motion of the crate. That crate could be moving pretty fast. I mean, it's what? It's 50 kilograms, it's got 3,200 joules. We've got to come back and see how to calculate how fast it's moving. But it's all going into kinetic energy. Now, as a comparison, and we'll look at this example in more detail in a moment here, but very quickly, if there was a frictional force, how would that change things? You go, well, it's just one more force, I just add that to my list. So I add that to my force diagram, and it's going in that direction. It gets added to my list as a friction. Now, if I've got a frictional force going this way, and the displacement is in exactly the opposite direction, what do you think? Is that transferring energy? Is there work being done by friction? And it turns out that if you have forces opposing the motion, those are transferring energy out of the object, right? So let's think about that. We had transferred a force F, specifically the cosine theta component, transferred in 3,200 joules. Well, what if friction transfers out 3,200 joules? Then what's the net increase in energy of the object? You go, in that case, it's 0, right? If I transfer 3,200 joules in, and nothing's taking any energy away, then the thing's going to be moving fast. If I transfer 3,200 joules of energy in with this force, but friction removes 3,200 joules, it's not picking up speed. If friction takes out energy, every time we put some energy in, friction takes the energy out, then we won't be going any faster. And we can tell which forces are putting energy in, which forces are taking energy out. That's going to be determined whether the force is in the direction of displacement. Forces in the direction of displacement put energy in. Forces exactly opposite take energy out. Okay. And then you go, well, what happens if the forces are kind of at an angle? Well, if the force is at an angle, we break it into components. and then one of those components will not be transferring energy, but the other one will be involved in energy transfers. Okay. So it's weird. I understand these are some new concepts, but go through this, practice some of these examples, talk to yourself as you're going through the examples and tell yourself what's going on in terms of energy. So what happens a lot of times when we get into these chapters of chapter 7 and 8, chapters introducing energy, sometimes students have done really well in the kinematics and the forces, and they've gotten so good at working with forces, they're a little hesitant. They're going, well, why should I learn this energy stuff? I already know how to solve all these problems using forces. It sounds like we're just making up some new words for things. It turns out that using energy as a way to solve some of these problems, it's a very powerful technique. So we're going to find situations where it's going to be more difficult to identify exactly how all the forces are acting on the object. But often we can still solve a problem because we can analyze the energy transfers that are taking place. Okay, so my advice, my encouragement here for you guys is embrace this new idea of energy. Start trying to use energy in the calculations. Definitely go back, and if you see a problem and you go, well, I could have calculated that back in chapter 4, go back and calculate it using the techniques from chapter 4. But also use the new techniques, the energy techniques, in chapters 7 and 8. So here's the recommendations. Draw a free body diagram when we're doing problems involving this. We've been doing that. Pick a coordinate system. We've been doing that. Apply Newton's laws to identify any unknown forces. Now I think what they're doing is they're thinking in terms of friction, or they're thinking in terms of normal forces and gravitational forces. How are they related? And then, now here it says, find the work done by a specific force. I'm going to say list all the forces, and then one by one, go through the list of, because that's what I'm going to ask you in the midterm. Create a list of forces, identify which ones are transferring energy and which ones are not. So, find the work being done by each specific force. To find the net work, add all of that together. So once you've identified how much work is being done by each force, you can just add the numbers up. Force diagrams are vectors. So the forces are vectors, and for that you got to keep track of directions and components. But work, it's either energy going in or it's energy coming out. And there's no direction associated with that. So I don't have to think in terms of X, Y, Z components. I just have to know how much energy is going in, how much energy is being taken out. So let's look at another example. These are tricky examples, I think. This is kind of like the grocery bag thing, right? Now with the grocery bag thing, the way we solved that was, or we thought about it, was if a person's moving at constant velocity on the level, you're not really transferring any energy in. The grocery bag keeps moving with the same kinetic energy, the same velocity, the whole time. So this is a little different because it's kind of like the grocery bag, except now we are going up an incline. Now what they also threw at us this time, they put the theta in a funny place. I don't remember we ever put theta there. Whenever we had an incline, didn't we define this as the angle of incline? So that's throwing me off, but we'll watch for that when we go through and take a look. Now, what they want us to figure out is, did this backpacker, this hiker, did they do any work? Did they transfer any energy to their backpack? Okay, so now I'm thinking this, how fast was the backpack moving at the bottom? And how fast was the backpack moving at the top? And what we can do is we can use that same idea before. They didn't specify, let me read the whole problem. Oh, right at the very bottom. They say, for simplicity, assume the motion is smooth at constant velocity. Now it turns out that that's very good advice. So if they tell you specifically that the person's speed at the top is essentially the same as the speed at the bottom, so the backpack isn't going any faster, then we just go ahead and for simplicity we assume that it's a constant velocity. Now you got to watch for problems. In other problems, there could be a designated, a specific acceleration that's identified. But in this case, it doesn't seem like it. Now, this backpacker, this person is going to carry the backpack up a hill with a height of 10 meters. Now, that's the height. Don't we need to find a displacement? It seems like what we talked about before was displacements. So, and we can do that. I mean, did they give us an angle? Oh, they didn't give us an angle. Okay, so all we know is the height. And here's an angle here. Now here's the backpack. We've isolated the backpack. There's two forces acting on the backpack. There is gravity, mg, and then there is the force lifting the backpack upwards, and that's coming from the person. So the person, you know, it's either from the shoulder here, I guess, in this case, mostly coming from the shoulder. If they had a hip strap, maybe it's you know, you're trying to create more of that effect from lower from the hips. But this looks like it's just a shoulder pack exclusive. I wonder why they don't have a hip strap. Anyway, here is the backpack, and the force is upwards on this, and this is downwards. Now, again, this is going back to the idea of constant velocity. If we assume constant velocity, then there's no net force acting on this object. So as the person climbs the hill, the force they're exerting is exactly equal and opposite to the gravitational force. So the force they have to lift with matches the gravitational force, and it's exactly opposite in direction, so that's upwards. Even though the displacement is in this direction, that's not the direction of the force if it's a constant velocity. The force will be this direction. So this is actually a problem to stop and think about. Even, you know, this could be a chapter 4 example asking what the force diagram should look like for this example. And the force diagram looks like this, if it's constant velocity. All right, now here's the picture down here. Now they've taken the two forces and they're adding in the displacement. So the question becomes, which of these forces has a component in the direction of the displacement? Now there's a couple things we could do here. We could break these forces into components. Clearly these forces are not perpendicular. So there's going to be some connection between the forces and the direction. Now what we could do is we could take the forces, divide them into components, find out how much of the component is in the direction of displacement. Another thing we could do, now this is another way to think about it, instead of dividing the forces into components, what if we divide the displacement into components? So we could say that this displacement consists of two components. There is a horizontal component. So horizontally, the displacement looks like this, and that would be d sine theta, because this is the opposite. But there's also a vertical component to displacement, and that would be d cosine theta, and that would equal h. So it turns out that h may actually be the important quantity here, because h is the displacement in the direction of the forces. So I would say that's what we want to be doing here, is taking a look at the displacement and seeing how that's going to be related. So here's the triangle that we had set up. Here is d, here is theta, here is h. Now it says that the backpack, I hope I got all these right, the backpack is 15.0 kilograms, and we're assuming Earth. So we're going to assume Earth's gravitational field, 9.80 newtons per kilogram. Now, we said for the majority of these, not always, but in most of these types of problems we look at, they're assuming just a constant velocity. So, and so the acceleration is 0, and that would say that the upward force matches the gravitational force. I can calculate how large that would need to be. The gravitational force is 147 newtons. And that means the person pushing up on the backpack, that's also going to be 147 newtons. Now, a pound is about 4 or 5 newtons, so what do we got? That's like a 30-pound backpack, something like that. So 30 pounds, 147 newton backpack that we've got here. Now the H value was given as 10 meters, and they never gave us an angle. So they didn't tell us if we're like walking up something super steep, or if it's just a gradual incline over, a kilometer, and we've only gained 10 meters of elevation. But in any case, let's go in and see what we've got then. So if we think about it that way, if we think about it, well, what if we take the displacement and divide it into vertical and horizontal displacements? So the work being done, the energy being transferred by the force of the shoulders, the backpack, lifting up on the backpack, that's going to be a force of 147 newtons, and by the time the hiker is all the way to the top of that incline, they will have displaced a distance of 10 meters vertically. Now, we never went in and solved for how far they had displaced horizontally. They just didn't give us that information. I should have added something in. I didn't. That would have been useful to think about. But in any case, it's 147 newtons. And since the force was vertical, I'm only including the vertical displacement. And that says it was 1,470 joules. So that's the energy transferred into the backpack. Okay, now the hiker may have exerted more energy than just the energy responsible for lifting the backpack. But to get the backpack from this lower elevation to this higher elevation required that much energy. That particular moving the backpack from here to there required 1,470 joules. So what about gravity? What's gravity doing the whole time? Well, gravity then would be, now I wrote this, and I should have done all this, I don't know that we needed to do this. Let's see. Let's get back to this triangle. I mean, I think what's here is fine, but let's get back to the triangle here. So the work being done by this vertical force is going to be F times d cosine theta, because d cosine theta is the component of the displacement. Okay, so d cosine theta is the same thing as h, and that's why we said we can just include the vertical component. Now, the energy being done by gravity then is going to be the opposite of that, the negative of that. Like we talked about in that slide before, if I have a displacement in this direction that's exactly opposite of force, gravity is taking energy away. So gravity is taking energy out from that object. Gravity actually stores energy. And so we'll see this in the next chapter. We're going to be talking about something called potential energy. So we're going to get to that. But gravity in this example, where we're just looking at energy transfers, is taking energy out. And the amount of energy it's taking out is mgh. Now I wrote that in here as mgd. Let's see. So if mg is here and d is here, then I could say that it's mg times d times the cosine of this angle. So, but the cosine of this angle is the cosine of 180 minus theta. And if it's cosine of 180 minus theta, that's minus the cosine of theta. You can go through these trig relationships, or you can just break it into components. So I think that's the easier approach. Just break into components, and since the forces are vertical, only the vertical displacement will come into the calculations. So the gravitational force is taking out the 1,470 joules, and as I just mentioned, that's going to go into something that we're going to label as gravitational potential energy. So that means on the way back down, gravity can transfer energy back into the backpack. Now, what's the net work on this backpack then? And it's 0. And the fact that the net work is 0, we put 1,470 joules in, gravity took 1,470 joules out. That means it's just traveling at a constant velocity and it's not picking up any kinetic energy. So it's not going faster, it's not going slower, it's just maintaining a steady speed the whole time. Now, what about this displacement? So I had this horizontal displacement. Is there any work, is there any energy transfer associated with the horizontal displacement? And you go, not if it's constant velocity. If it's constant velocity, then even though we're having displacements in the x direction, there are no forces in that direction. The backpack is just steadily moving in that direction, but it doesn't require a force. Vertical direction, it does require a force because I've got gravity acting on it. All right. So, questions on any of that? So these are the concepts that we're developing here, and kind of the talking about what we mean by all of these things. So let's see, and I think this is just confirming or reinforcing the idea that when I'm working with this formula, when I say that the work being done by force, the energy transfer being done by force F is F times d times the cosine of theta, what we're doing is saying that the d now, there we go, the d now is being broken up into vertical and horizontal components, and we only have to use the vertical component. So the magnitude of the force times the magnitude of the displacement, they're in the same direction. That's adding energy in. Energy is that's the addition of energy to the object, and this is the removal of energy with the gravitational force. Okay. All right. Now, here is an interesting question. Here's Earth, here is Moon, and Moon is orbiting Earth. So Moon orbits Earth, and this takes us back to Chapter 5, Circular Motion. I hope that is familiar. I hope that you guys, as you move on, that these things are remain kind of familiar from one chapter to the next. It's like, wait, weren't we through with that chapter? No, physics is just cumulative, right? You have to, everything just gets built on what you've done in the previous chapters. So we do want to intentionally come back and, check out everything that we've looked at before. In this case, we're checking out circular motion. There's a force of gravity. And the force of gravity, chapters 5 and 6. So the force of gravity is attracting towards, the Earth, and we can treat the force as being directed from center of mass of the Moon towards center of mass of Earth. Let's assume for a minute that the Moon's orbit is exactly circular. If Moon's orbit is exactly circular, then that would say that the displacement, every time the Moon moves a little bit, its displacement is always perpendicular to the force. So if the force and displacement remain perpendicular at all times, is any energy being transferred? And you go, no. You go, wait a minute, but there's a force acting on it. Shouldn't energy be transferred? And you go, no. In many situations, forces are not transferring energy. Only when either the forces are causing the object to speed up or slow down, or changing their elevation. That's what we saw in the last example, where energy had to go in to lift it through a gravitational field. And so, in this case, the Moon is not picking up speed. There is no force in the direction of the displacement, and that means that the Moon just maintains constant velocity. If the velocity is constant, then the kinetic energy is constant. The kinetic energy is not increasing in the Moon. The Moon just keeps traveling at the same speed. So it's a nice example. I like the example because it kind of forces you to think, oh yeah, even when you've got something moving and forces are acting on it, it doesn't mean energy is being transferred in that case. So let's see what they ask us to do. They just ask us to say, does gravity do any positive work on the moon, any negative work, or no work at all? No work at all if the orbit's circular. Now remember from chapter 6, orbits aren't entirely circular, right? The orbits that we see, almost pretty much every orbit that we look at has a little bit, at least, of eccentricity to it. Doesn't have to be a lot. It could be a little elliptical in nature. So in that case, there would be periods during the orbit where the moon speeds up, and other parts of the moon's orbit where it's slowing down. And during the times where it's speeding up and slowing down, when it's speeding up, gravity's transferring energy in. When it is slowing down, gravity's transferring energy out. So there would be times when the work would be listed as positive, times when it would be listed as negative, and then there would also be times during the moon's orbit, if it's an ellipse, if it's elliptical, where the work would be zero, if the velocity is perpendicular to the force of gravity. And here's kind of a reinforcement of that. So here's Earth, here's my diagram. mg is in this direction, or I guess I could have done big G, big M, little m, over distance squared. The G here is not 9.8. You guys understand that, right? So I would have to calculate the gravitational field, and then measure by measuring the distance between the center of the Earth out to where the center of Moon is. But that's mg, and then the displacements. Now notice it's circular motion, so I have to really think in terms of each displacement is shifted a little bit from the displacement before. So I've got to use a series of little infinitesimal displacements. I use ds for that. I think that's a common notation in math books. So, a little ds, 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 ds. The force remains perpendicular if the orbit's circular. If the orbit is circular, then at every location the displacements are perpendicular to mg, and that says that there's no energy being transferred. All right, we are ready to dive into a more detailed definition for energy transfer, for work. What we're going to do is we're going to introduce an operation of vectors, and it's called the dot product. It turns out that when we write down something as a dot product, it turns out that taking the dot product of two vectors, here it's just vector A and vector B, is the magnitude of A times the magnitude of B times the cosine of the angle between them. So here's the diagram right here, right? And what it's saying is here's a vector of some type, and here's a vector of another type. Now they don't have to be the same physical quantity. In fact, in general, they're not. So what we've been looking at is force and displacement. And it turns out that that's going to be the first example of using our newly defined dot product. Now you may have seen this in calculus class. I think it's in Calc 3 where they do vector calculus and they introduce dot products. And there's only going to be two of these that we run into. The dot product, and then when we do circular motion and look at torques, we're going to introduce what's called a cross product. And we'll get to that. But the operation, the vector operation that we're going to define right now is, you can think of work as kind of an example of this. Energy transfer is F dot D, where F dot D means the magnitude of the force times the magnitude of the distance times the cosine of the angle between them. Now we know that cosine of theta between the two vectors, what that's going to give us is it's going to give us the component of one vector in the direction of the other vector. Okay. Now what we've seen with work already is we can divide the force vector into components, or we can divide, we can break up the displacement vector into components. So we can, and in either case, we ended up with the same formula. And so let's see what some other properties of this dot product. Oh, I think maybe that's it. Maybe that's all the depth that we're going to go into with the dot product. Okay, so let's go ahead and use an example here and practice using. There we go. Practice using the dot product. It says that we're pulling with a force. Oh, this is starting to look familiar, right? The magnitude here is only 20 newtons. That's not much. That's like 4 or 5 pounds of force. It makes an angle of 30 degrees. So someone's pulling on this wagon at an angle of 30 degrees. Calculate the work, the energy transfer, being done by this force. But this time we're going to use the dot product definition. And it says that the wagon is going to be dragged. I hope the wheels are rolling. It's not one of those shopping carts from the store, is it? So the wheels, this is frictionless. The wheels are going to be rolling, and we're going to drag it 100 meters. Oh, maybe not. Maybe there is friction here, huh? Because otherwise, this wagon's going to be going fast. It's going to be picking up speed. I think they're just isolating one force. In any case, let's go in and see how this would work. So what we would start with now is our new definition of dot product. Isn't that amazing? It's going to impress your friends. Your friends will be looking and going, wow, what the heck is that? You go, it's a vector dot product. Now, when we do a vector dot product, what that gives us is a scalar quantity. That's kind of interesting. I took two vectors and I combined their components, in a way where I just have a scalar left. Okay, it used to be two vectors, but now I've turned it into something that is a scalar quantity. So, again, the dot product is the same thing as taking one of the vectors, breaking it into components, and then taking the component of the force that aligns with the displacement. And so it's still just FD cosine theta. We write in F, we write in D, we write in theta, and I put all the values together, and it turned out to be 1,732 joules of energy being transferred. Okay, so when they said, use the dot product to solve this, I did. I used it right there. I wrote down two vectors, I put a little dot in the middle. So the dot here is supposed to suggest multiplication, but what's being multiplied here are the combinations of different components. So it is multiplicative, but it's a certain set of rules for how to multiply things together. Okay, we are ready now to, now that we've talked about the dot product a bit, to move up to varying forces. Forces that either are changing in direction or changing in magnitude. So they're not pointing necessarily in the same direction, or the force isn't as large. Now this diagram is kind of complicated because look, there's a force here, and then a force here, and then the force tips, and then it tips back, and then it's here, and then it's here. How would I calculate the amount of work being done? How would I go in and determine the energy transfer that's taking place? And so what we would need to do is we would need to take each individual displacement. Well, this force acted and during this displacement, and this force during this, and this force, and there were so many forces we didn't even write all the label them all. But here are all the displacements that took place. And from getting to A to B, we could go in and we'd have to know a lot of information, right? We'd have to know the force at each step along the way, and then we would have to know the displacement at each step, and then what else would we need to know? Right, so what we would also need to know is the angle between those at each step. So they only wrote one of the thetas in here. There's a theta 2, 3, 4, oh, there's theta 5, theta 6, theta 7. We could add it all together. Now what is that starting to sound like to you? And I know you're starting to think, oh yeah, this is like calculus, right? So what we could do is we could approximate energy transfers by breaking up the displacement into a bunch of short distances and then multiplying each one by the component of force at that location. Okay? See how that lines up with everything we've talked about so far. So if you rushed through those, the early part of this, and you were going, oh, this isn't going to be that complicated, you might have to go back and review, but that's the amount of force in the direction of displacement, and that's the displacement at each step. Now what they've done is they put this on a graph, and you want to be able to do these graphs. So this is saying, how much of a component of force is in the direction of displacement for each of the individual steps. Now notice they didn't even start at point 0. Here's point A and here's point B. So what they're doing is they're creating a histogram, and now they're going to say, well, if we took shorter and shorter steps, this could be written down as an integration. So that's going to be the general formula we're going to get to here. Ooh, there it is. Isn't that pretty? So there's that integration sign. So it says we can follow a path from point A to point B, and we have to find some way of designating what that path is mathematically. And then we can keep track of the force along that direction. Well, if I have a force times the cosine of theta times the displacement, what I could do, I could write that as a dot product. So it's a dot product between a force and an infinitesimal displacement. And I can add all of those together, and so that's our general formula. So at first we were doing, those first examples we've been working through, getting an idea of how this all works, and now we're taking it down to what happens if the force is changing. So what if I have a force that behaves like this, specifically the component of force in the direction of motion, and we can integrate that. And that means that when I do a diagram of force, parallel force, versus displacement, what's that area under the curve? And that area under the curve is work, or energy transferred. So the area under the curve will tell us how much energy we have transferred during that process. That's handy. So there's going to be situations where we have to, you have to go into the lab. Maybe nobody's going to give you a formula for the force. You have to go into the lab and find out how much force on a mechanical system that you've developed, and measure how much force you're applying at each step, measure the displacements, plot it on a graph, and then you can color that in and find out what the area is. That's how much energy it's going to take to exert that force over that distance for that device. All right, so I'm thinking that might actually be a good place to kind of wrap things up for today. So that's kind of the first half of the chapter. Let me say this, where we're headed is we're going to be looking at work being done with varying forces. We now have kind of the mathematics in place. We could go through and look at some examples of calculating how much energy we're transferring for, we'll start out with some, what I hope are some fairly simple cases. We're going to start out with a spring, and we're going to say when we compress springs, when we either compress a spring or if we stretch a spring out, that's going to require energy. That's going to require work to do that. And springs are going to be storing energy, and so this is also going to become a source of what we call potential energy. Energy being stored in a device, or energy being stored as a result of lifting something. We saw gravitational potential energy. So this is going to be another way that we can store energy, and we'll introduce the idea of ideal springs. So something to look forward to. So any questions on this chapter or any of the earlier chapters, stop by office hours and we will get those looked at. All right, have a good day. Ooh, one last thing. Actually, we do have a few more minutes here, so I'm gonna get a little bit more of this example going. So here's a spring, and sorry about that. You guys probably turned this video off already, right? But here is a little bit of a start on this example, and then we'll come back and pick up in any case. So here's the spring where it is unstretched. So here's the spring, and what we're going to do is we're going to attach the spring on this side, and then we'll leave this side of the spring free in this example. We're going to call that x equals 0. So that's going to become important in setting up our coordinate systems. So we want to set up a coordinate system in a way where x equals 0 represents kind of an equilibrium. It's the unstretched length of the spring. Now, if I stretch it out some distance, that is what's going to get called x. So what this is telling us is, well, how much force is going to be required to pull the spring out some distance x. And so what the diagram is showing is I started with the spring, and then I pulled it, and I pulled a little farther, and I pulled a little farther, and right now it's out here at this location x. Now I'm holding it with enough force to offset the force of the spring itself. So the spring itself is pulling on my hand, and it's pulling with an amount that's proportional to displacement. That makes it an ideal spring. Now, many springs actually follow this, pretty well. And so, but mathematically, it's easiest to start out with the assumption that the force of the spring is directly proportional to how much we've stretched the spring. And so the minus sign here is keeping track of the fact that if x is positive, let's say that stretching it out is defined as the positive direction, well, the force of the spring pulling on my hand will be in the negative direction. What happens instead if we compress an ideal spring? Well, this formula still works. So if we compress it, what we do is we define that as the negative x direction. Now x has a negative value to it. And if x is negative and the k value is positive, this minus sign cancels that and says the force will be in the positive direction. So the way this works is if x is in the positive direction, the force is in the negative direction. If the x is in the negative direction, the force is in the positive direction. And so that's what that minus sign is keeping track of. Now, one thing to keep track of, and I think this is important, a lot of times, students will just write the formula down, go, okay, the force due to a spring is minus kx. Sometimes in these examples, we're not really interested in the force on the spring. We're more interested in the force being provided by, in this case, the hand. So the force due to the hand is opposite. So if we wrote the force due to the hand, that would not have the minus sign. So be prepared. You can't just write the minus sign down and, absent-mindedly and go, yeah, it's always, the formula is F equals minus kx, because it could be kx. It could be plus kx or minus kx in an example. I'll try and point those out as we go through some of the examples. Now, this is something that we call a restoring force. We'll see this in later chapters when we look at oscillations. This is something that brings the spring back. There's a force tending to pull the spring back to its natural length. So the spring is trying to get back to where it started. Now the force constant, the little k value, is going to have units of newtons per meter. Okay. So a little bit of introduction to springs and their forces. Again, any questions, stop by and we'll get those looked at.